good morning, everyone. Let's
Morning.
start. Okay, so yesterday we were discussing PCA. Today we'll try to implement it in Python notebook. I'm sharing the file over chat. So the first part is where we will be importing this iris dataset. It's a very famous dataset in which, based on the sepal length, sepal width, petal width, right? We try to see which variable, which kind of flower it is. So I think there are three types of flower it has. We try to see which kind of flower it is based on the length, width, and of petal and sepal. So we are just importing data from this link. And if you look at the data set, it has values for length and width of sepal and petal. And we have three classes: Setosa, Versicolor, Virginica, right? These three classes are there. Now, PCA is also a distance-based algorithm, okay? Because, if I would have to give an example, just 1 minute. Right. Now, not sure why my pen is not visible. This one.
Sir, can you give quick recap of PCA?
Okay, so in PCA, what we do is, okay, let me just follow the slides itself. Okay, so we started with this thing that in general, when we have too many, like when we do not have enough experience in machine learning, we just assume that if we will have a lot of variables, that will be good for us. We will be able to create a very good model. Okay, to some extent, that thing is true. More the number of variables actually can help you in predicting the target variable better. But the problem is when we have too many variables, okay? And how do we define too many variables, right? Too many variables are all, like when we say too many variables, it is always defined in terms of number of rows, okay? Now, if I have 100 rows, even 10 variables are a lot of variables, okay? Because there are 10 columns and there are 100 rows. On the other hand, if I have 10 columns and I have 10,000 rows, then 10 variables is totally fine. No problem over there. Similarly, if I have 500 variables and 10,000 rows, then 500 variables are a lot of variables. But if I have 500 variables and I have 10 crore rows, then 500 variables are not too many. Okay. So when we say too many variables will lead to overfitting, okay, we say it in terms of number of rows. Okay. The same number of variables can be too many. At the same time, it can be fine depending upon how many rows we have. Right. So if I have 10, I will just repeat. If I have 10 variables and I have 100 rows, even 10 variables are too much. But if I have 10 variables and I have, let's say, 10,000 rows, then 10 variables is totally fine. If I have 500 variables and I have 10,000 rows, again, 500 variables are too many. But if I have 500 variables and I have 10 crore rows, right, then 500 variables are fine. Okay, so there is nothing like that. If the number of variables will be more than 100, it will always be too many. No. Whether the number of variables are too much or not, it is always defined in terms of number of rows in the data set. That is one thing. Second thing is, what is the problem with having too many variables? If we have too many variables, the problem is that there is high chance that the model might overfit. Okay. Similarly to if I have two less variables, if I have very few variables, there is a high chance that the model will underfit. If I have too many variables, then there is a high chance that the model might overfit. Okay. So to avoid the problem of overfitting, what do is we use PCA. What PCA does is PCA combines different variables, okay, and create new variables. So if I will give 3 variables as the input, PCA will give 3 variables as an output. Okay. But if I'm giving 3 variables as input and getting 3 variables as output, then where I'm reducing the number of variables. Okay. If I'm giving 3 variables as input and getting 3 variables as output, then the number of variables are 3 only. Right? So where is the difference? The difference is in terms of how the information is distributed. In first case, first variable was 40% important, second variable was 35% important, third variable was 25% important. So if all the 3 variables together are giving you 95% accuracy, hypothetically, okay, if it is giving you 95% accuracy, then if you will drop one variable, then your accuracy might reduce to only 80%. Why? Because X3 variable is not very less significant. Okay, it is not insignificant. X3 variable is also contributing significantly. But when you look at PC1, PC2, PC3, how importance is distributed? 70%, 25%, 5%. It means that first variable is 70% important, second variable is 25%, and third variable is 5% important. Okay, now if I will remove one of the variable, if I'll use all 3, I will get 95%, same as what I was getting earlier, because there is no information loss. But if I will remove one variable, let's say if I will remove PC3, then what will happen is, in the first case, when I was removing X3, my accuracy was reducing from 90%, 95% to 80%. But in this case, if I will remove PC3, my accuracy will only drop from 95% to 93%. So I'm being able to reduce the number of variables. Okay. And, I'm being able to reduce the number of variables, but at the same time, my accuracy is more or less same. Okay. So that's the benefit of we having, we using principal component instead of using original variables. But what is the drawback? The drawback is principal components are defined in this way. The first principal component, something like this. Like in the backend, it works like this. PC1 will be combination of all 3, PC2 again, PC3 again. Now earlier, if each variable had some definition, I can say x1 is height of mother, x2 is height of father, x3 is height of grandparents. Okay. PC1, PC2, PC3, I cannot give them any name. I cannot define these variables. These are just variables, but what is the meaning of it? I don't know. Okay, so that is one disadvantage of using principal component. Okay, then I was saying that principal component is a distance-based algorithm. What do I mean by it is a distance-based algorithm? Let's see. Okay, now let's assume we have some data points. Okay, this is variable 1. This is variable 2. Now, if I will look at the range of variable 2, the range of variable 2 is from this point to this point. Is that right? This is the minimum and maximum value of variable 2,
Yes.
right? Similarly, now if someone will ask me, what is the range of variable 1? Variable 1 ranges this thing and this thing. Okay. Now let's say this variable 1 is some variable like maybe salary. This is salary in thousands. Right? And let's say this is sugar level. We are trying to, let's say, check if there is a relationship between sugar level of a person and salary of a person, right? Now, can when we have variables like this, variable 1 and variable 2, both the variables are important. Why? Because variable 1 is also having a range, variable 2 is also having a range. Okay, so I cannot simply discard any one of the variables. Okay, how PCA works is it rotates the axis in such a way that if earlier, let's say here, this was the range of variable 1, the variable 1 also had some range, variable 2 also had some range, right? Variable 1 was also varying, variable 2 was also varying. PC rotated the axis in such a way, right, that the variation along one of the axes is almost negligible, right? One of the values become almost constant. So the importance of that variable will go down. Now, there is another way of doing it. What is another way of doing it? Maybe what I can do is, I can say that instead of putting salary in thousands, I want to put salary in, for the same people, I want to put salary in millions. Okay. Here I was putting salary in thousands. Let's say if you are earning 10,000, 15,000, 20,000 per month. Here I am putting salary in million. Now, what will happen? Will the value reduce or will the value increase? Let's say if there were different people, let's say person 1, person 2, 3, 4, 5. If someone was earning 10,000, then the salary in thousands will be how much? 10. 10,
10.
right? If someone is earning 15,000, then the salary in thousands will be
15.
15, right? Similarly, if someone is earning 8,000, the value will be A. Someone is earning 18,000, the value will be 18. 20,000, the value will be 20. Okay, so that is what the case is as of now. What we have done is we have put salary in thousands. But what if I will put salary in millions? Then instead of dividing it by 1,000, I will divide it by 10 lakh. Okay, then the value might become something like 0.01, 0.015, 0.008, 0.018, 0.020, something like this. If I will put salaries in millions instead of 1,000, then what will happen? This y-axis that you see, that will reduce, right? Now all of these values will come very close to each other, right? Here, almost all the values will come over here. Okay, the value of y2 will remain same, but value of v1, this is how it will look like. Almost all the values will look like 0. Sorry, my bad. Is that correct? This is how the values will look like now. If earlier it was looking like this, assuming, let's say, this is like something like this is 5, this is 10, 15, 20, right? If I'll put the same values here, 5, 10, 15, 20. Now the values will look like this. So can I say that now variability in variable 1 is very less and hence it can be removed? For variable 2, it is still varying from, this point to this point in both the cases. But for variable 1, now there is not much variability. So can I remove variable 1 now?
Yes.
Right? No. That will not be correct. Why it will not be correct? Because there is variability in the data. It's just that you have put the scale of these very differently. Right? In this way, I can reduce any variable. I could have reduced V2 as well in the similar way. Right? If I will change the units of V2, right, it might come that all of these points will come together. Just like all these points have come together across V1. Right? So it is important when we are doing PCA that we standardize the variables. Okay, it is also a distance-based algorithm. We should standardize the variables when we are doing PCA so that the units does not impact how your data is distributed. Here the data is distributed a lot, Here the data is not distributed much. Why that is happening? Just because of the units of variable 1. Okay. So what do we want to do is, we want to make sure that these kind of things should not happen. And to do that, we want to standardize the variables. All the variables should be standardized. And how the variables can be standardized? Using either standardization or normalization. Both is fine. But the range should be similar for the two variables. Okay. Only then PCA can work. So the first step is always in PCA to standardize the variables. Okay. Let's see here. What we have done is we have standardized the variables. Now, if you look at earlier, the values was like 5, 3, 1, 0.2, like something like this. Now, if I will look at standardizing the feature X. Oh, this is the array. This is not a. This is not a, what I should say, data frame, right? So let me. Here we have changed it to a data frame already. This is a array. That's why this didn't work. Okay. So once we did use standard scalar, it became an array instead of data frame. In the next part, what I'm doing is I'm converting it to a data frame first. Okay. So if I look at this data frame, just 1 minute.
Puneet, just
No,
a
no, no.
question.
Oh, yeah, tell me.
If the relationship between variable 1 and variable 2 is something in parabolic or any other curve instead of linear, so in that case also will this work?
Yeah, this will work. It's just that depending upon what kind of data set it is, right? Let's say, for example, here, let me create a copy of it. So here the distribution was, here the distribution was 40, 35, 25. After using PCA, it became 70, 25, 5. It could have also been the case that maybe after doing the transformation, it might not change much. It might only remain, it was earlier 40, now it is 42%. If it's 35, it is 37%. And then this will be, I believe, 21%. This can also be the case. In this case, the PCA is not helping you much. Okay. Or it could have been something like this as well, that maybe PC1 itself is giving you 90%. This one is giving you 8%. And this one is giving you 2%. So here PCA is doing very good. Okay. Or what can happen is, let's say what we put it here, 70, 25, 5. 75%, 25%, 5%. So here the PCA performance is as expected, not very good, not very bad, but as expected, right? So there can be a case where the PCA is not working altogether, like this 42%, this 42%, 37%, 21%. So PCA is not working at all. Although I have used PCA, but because how the data was distributed, I'm not being able to reduce the variables. Or it can be the case where it is working so well that maybe I need to use only one variable. The remaining two variables, if I want, I can drop. Or maybe it will work in a way that maybe I can remove one variable but not two variables.
Okay, yeah, got it.
Okay, so the example of parabola that you have given, there we can use PCA, but it may or may not be able to reduce the variables.
Okay.
Okay, so here if you look at it, what I am doing is I am mentioning that how many principal components I want, right? So how many different variables we had? We had 1, 2, 3, 4. We had 4 different variables. Corresponding to these 4 different variables, how many principal components should be there?
4.
4, right? But I can mention that, okay, give me the only top 2. I will change it later. I'll show you later. But I'm saying that I can mention that I, only need the top 2 variables. I don't need all, right? So if I will do that, this is how the final data set will look like. You have principal component 1, you have principal component 2, and you have a target variable, right? Like just like earlier, your data set had what? You had 4 variables, variable 1, 2, 3, 4, and a target variable. So 4 input variable and a target variable. Here, how many input variables we have now? 1, 2, and a target variable. So the number of variables I have taken reduced from 4 to 2. But now I want to see how much of a information loss that will happen. Okay. Let's discuss this first, this part first. Okay. Now, when I'm running this, it is telling me how much each principal component is explaining the variability. Let's say this thing, 42%, 37%, 21%. This is that number. So the 2 principal components that I have created here, right? Principal component 1 and principal component 1. Together, how much they are explaining? How much?
91%.
Right? So it is 73% plus 23, right? So it will be around 96%, right? So 4 variables, if together was explaining 100% variability, these 2 variables are together being able to explain 96% of the variability in the data, right? Here I had hard coded and said that I want only 2 principal components. But actually, ideally, how we should do is we should do it using 3 plot. What is this? So what I will do is, so one way of doing principal component was where I mentioned that I need 2 principal components. That is one way of doing it. Another way of doing it is same function. Same function, if you look at it, I'm using later also. Here I am mentioning, give me those many principal components which are explaining at least 95% variability. Okay, what is the meaning of that? Let's say over here, if I will say that if this is the case, and I will say that give me those many principal components which explains at least 95% variability, right? Then I will end up selecting all the 3 principal components. Why? Because 42 plus 37, how much it will be? 79%,
Yeah.
which is less than 95%. So I need to bring one more. So all 3 principal components will get selected. Here, 90 plus 8, 2 principal components together are explaining 98% variability. So if I'm keeping my cutoff as 95%, then these 2 together will be able to give me more than 95. So I'm fine. Similarly, over here as well, right? I think this number is not correct. Right? 75 plus 25 plus 5. No, should be 20. Here, for example, together, they are being able to explain 95% variability. So here, only 2 of these will get selected. Okay, so I can find a principal component in this way also, that give me the number of principal components which are explaining at least 95% variability. Okay. So if I will run this one, it is telling me you will need at least 2 principal components to explain 95% variability, right? Because I know that the summation of these 2 is how much? 96%. So if you want at least 95%, these 2 together will work. What if I will make it 97%? Then what is your expected answer? will these two together be able to explain 97% variability?
No.
No,
No.
right? So I'm expecting at least more than two, so at least three, right? Let's see. Let's see. Now the number of principal components are three. If I will, again, hypothetically, if I will make it 70, then how many principal component it will give me?
One.
One, right? Because one single principal component will be able to explain more than 70%. Now it is one. Okay, so there are two ways, as I explained. Either you can mention yourself that these many principal components I want, or you can mention that I want to explain at least 95% variability in the data, and it will give you the number of principal components. Or there is one more way, right? Which I believe is a better way of doing it, which is using scree plot. What is scree plot? Scree plot is nothing but simply it tells me that one principal component, how much variability it is explaining, that is 73%. Okay. Second one is explaining 23%. Third one is explaining 4%. And fourth one is explaining 1%. So 73 plus 23, 96 plus 4 plus 1. So it is adding up to all the 101, right? Because, but if you will use the correct number of decimal places, this will add up to 100%. Okay, so it is telling you if those four variables, the original four variables, had an importance of 100, right? Then this one single variable will have a 73% importance. This will have 23% importance. So if I want to remove one variable, which variable I will remove?
The last one.
Last one, principal component 4. If I need to remove two variables, I will remove principal component 4 and principal component 3. If I need to remove three variables, then principal component 4, principal component 3, and then principal component 2, right? When you will remove the fourth principal component, there will hardly be any change in the accuracy of the model. It will not change much. When you will remove the third principal component, there will be a slight drop in accuracy. But if you will remove the second principal component, there will be a significant drop in the accuracy. Okay. So, and which one is the most important principal component? The first principal component. Okay. So using this plot as well, especially when we have a lot of variables, if you had 100 variables, right? Then in that case, I always feel you can maybe create this kind of a plot and see after which point the variables become insignificant. For example, in this case, I will say that this variable is insignificant. Okay. Only one problem with this approach, that here each variable had some meaning. For example, here each variable had some meaning. Sepal length has some meaning. Sepal width had some meaning. Same goes for petal length and petal width. But here, the principal component 1 or principal component, it does not have any meaning. So that's one drawback of using principal components.
So usually in how many if you have lots of variable on 10 will PCA, right? Or like what, like it's a four variable. I know you are getting, but in real time, when say you have how you decide you have to apply PCA or not?
Right, good question. So why we were applying PCA?
To
If I will,
read to reduce that overfitting and
exactly, right? Very nice. So the need of PCA arises from the problem that we were facing, that our model was overfitting. Okay. If the model is overfitting, like first thing is the model should overfit. There should be a problem to solve. Okay. So if my model is not overfitting, then we need not to do anything. But if my model is overfitting, that is on training data, I'm getting a very good accuracy. On test data, I'm getting a bad accuracy. Then that is a case of overfitting. In case of overfitting, what all different things we can do? We can maybe try a different machine learning technique. That also works sometimes. A few machine learning techniques are more prone to overfitting as compared to others. For example, decision tree or logistic regression will be more prone to overfitting as compared to random forest or XGBoost. Why that is the case? Can anyone tell me why that will be the case?
Do repeat the question.
I was saying that random forest and XGBoost are less prone to overfitting as compared to decision tree or logistic regression.
Because the number of iterations are more.
Very
Like in
nice.
case of decision tree. Yeah.
Right, exactly. In case of decision tree and logistic regression, there is one single model. Okay, so it can mug up, it can overfit, but in case of random forest and AdaBoost, there are multiple models which are coming together. That's why the results of AdaBoost and random forest are more generalized. Okay, that's one way of answering it. If someone had asked this question to you in an interview, if you know the answer, this is how you will explain. Just hypothetically, if you don't know the answer, okay, then focus on the question itself. The question is asking why random forest and AdaBoost is having lesser chance of overfitting as compared to decision trees or logistic regression. If someone will ask me this question in an interview, and if I don't know how to, like what to answer, then focus on the question. In the question, the two categories that he has created, that person has created is, one is, so the group one that the person created was random forest, and the second group that person, and AdaBoost, and in second group that person put decision tree and logistic regression. Okay, if I don't know what to answer, what I would have done was, I would have just simply told him what is the difference between this group 1 and group 2. If you look at group 1 as nothing but both the machine learning techniques are ensemble modeling techniques, right? Where multiple models come together to make the prediction. In group 2, both the machine learning techniques, right, are standalone models, like there is one single model only. So even if you don't know the answer, just focus on the question. You will realize that he has created the groups in such way. Then you can just simply answer that in group 1, I have ensemble models. Okay, and in group 2, I have these standalone models. And that's the reason that the group 1 will not overfit and group 2 will overfit. You got my point, what I'm trying to say. So even if I don't know the answer, you can just focus on the question and come up with the answer. Because in general, when we have these kind of questions, we just need to focus what is the difference between this group and this group. And even if you will tell the difference only, that answer will most probably be correct.
Puneet,
Yeah, tell me.
How to overcome underfitting issue if suppose my accuracy is only 50% or something like that. Like how can we overcome that?
Right. So for every question like this, right, the first answer that you can say is we can try a different machine learning technique. Okay. Even if it is a question of overfitting or it is a question of underfitting, for both, we can just simply say we can try a different machine learning technique. That is the first step. Second step is for underfitting. Why underfit happens?
Less data.
Data is less.
Yeah,
People.
right. Yes, exactly. The model is not being able to learn anything because there is nothing it can learn from. Okay, so that is the problem. When we say less data, we're talking about number of rows. Okay, or the problem can be, right, we do not have the right variables. like for example, the standard example that I take, if I'm trying to predict height of someone, the race and gender of that person is an important variable. If you don't have that variable, irrespective of how good machine learning technique that you use, you will not be able to predict the height accurately. If I don't have the age, the gender, and race of that person. Okay, so underfitting happens when your model is not being able to predict. Model is not being able to predict most of the time because of two reasons. One is either I don't have the relevant variables, or the second problem is that this is not my type of prediction. Like for example, logistic regression also used in the backend, linear regression. What does linear regression assume? What is the assumption of linear regression? What is the relationship between target and input variables?
That there is a linear relationship between.
Linear.
Right, very nice. So there is a linear relationship between the targets. Right?
Right.
Now, yeah, sorry. So now if the data set is in this way, right? If the data set is in this way, this is, let's say, my target, and this is my input variable, and the relationship is like this. Can, using my input variable, I predict my target? The answer is yes, right? I know that here in this case, y is equal to x square. So if you will give me the value of x, I will be able to predict y, right? But can I predict this target using linear regression? No. Okay, so this problem. Yeah, I'm putting everyone on mute. Okay, so in this case, it is easy to predict the target, but this is very difficult to predict the target using linear regression. Okay, so sometimes we need to change the machine learning technique. Sometimes we need to add more number of data points, and sometimes we need to add more number of variables. Okay, in case of underfitting, your first answer should be to change the machine learning technique and see if that is working or not. The second thing should be to add more relevant variables. Don't just say to add more number of variables. Okay, because a lot of people will get triggered on that. Adding more number of variables does not improve accuracy. Adding more number of relevant variables improve accuracy. Okay, so choose words wisely. Say we will be adding more number of relevant variable, and the third thing is adding more data.
Like,
Yeah,
is there any possibility if our approach is totally wrong, then the model will underfit? Like some days back, you told example of lens start cancellation and pseudo cancellation. If I am under assumption that only like if I only consider cancellation and not cancellation, and if I try to predict the model, that is there a chance that it will underfit?
No, actually, that's a very good point, Tejas. So when I answered the question, actually, I answered it from only one perspective, that is technical perspective, right? But I think yours is a very good point that we should also maybe think in terms of approach that we have taken. Very nice, yeah. That can also be the reason that maybe you have not defined your target variable correctly. Maybe I need to have different models for different market. Sometimes when you try to use the same model for all the markets like US, Europe, India, right? Then model might not perform good. But if you will break the data set, for US, you have, let's say, a separate data set. For Europe, you have a separate data set. For India, you have a separate data set. And then if you create 3 different models, that might be able to give you better results because each market can have its own trends. Okay, so yeah, that was a very nice point. Maybe the way you are designing the whole machine learning project, that can also be reviewed once.
So like one more thing. So if it's like underfitting, we need to check for the technical things. Like if data is huge and everything is huge, we should check from our concept wise, like clustering might happen or something else might be the reason, right? That's what you are trying to tell me, right?
Yeah, can you repeat the last part, like clustering and all?
I mean, you are telling, right, US, UK, the model, maybe the
Yeah,
data
that is
variables are correct. However,
huh,
our approach is different.
yeah.
That's where we need to do clustering and then apply the models so
No.
that they don't underfit anymore.
Yeah, Tejas, so your answer is correct, but the words are wrong here.
Yeah.
Like, see, if we are in an interview, if you will say anything, like maybe, the feelings that you had or the understanding that you had behind those sentences are correct, but we need to be also very correct with the words that we are choosing. When we say that we will split the data set by market, like it's US, Europe, and India, that is not clustering, right? In like a clustering word in itself in machine learning means something very different.
Okay.
Okay. This is not clustering. This is just grouping. Maybe you are grouping the
Yeah,
data
got
set into, right? Or you are splitting the data set. Even if you use the word, I should
Yeah,
split the data set, that is also correct. Why I'm
got it.
correcting you over here is because
I
a
got
lot,
you.
a lot many times it happens that we use the incorrect words, and that sometimes shows that maybe we don't have the right understanding.
Yes.
Okay,
Got it. Thank you.
sure. So, yeah, tell me.
One question. Last time you told right, like the PCA, right? So
Mhm,
if fraud detection, like you took
mhm,
an example,
mhm,
and we don't worry about whatever happened to the features. We don't understand the
mhm.
features, and
Right.
we can apply PCA in that case, right? And
Right.
but if something is a very domain specific and you understand the domain,
Mhm.
so you just want to know how each feature is affecting the model,
Right.
right? So PCA can be applied so blindly you can apply PCA if you are not worried about the features, right? Like is this correct? Like say
No, no,
like
you are right. You're right that if I'm not worried about the features, I can apply PCA. But again, in PCA, there will be some information loss. Like
yeah.
here, if I select the first two variables, the information, there's a 5% information loss. Okay. It means that
Mm,
if I will use all the four variables, then if my accuracy is 95%, if I will use only two variables, then the accuracy might reduce to 91% or 92%. Okay. So
okay.
by reducing the number of variables, I am overcoming the problem of overfitting, but that is
Okay.
also going to take hit on my accuracy, right?
Okay.
So if
Yeah.
you do not have a problem of overfitting, and if you will still use PCA, then you will unnecessarily be reducing your model accuracy, right? Because there is an information loss. Here, there is a 5% information loss
No,
if I will use only first two variables.
no. I'm saying like it will loss. I know it once you apply PCA, I'll know right loss or not. Then I take a call, right? Like
No, there
I'll
will always be a loss, right? It cannot be
yeah.
that there is no loss altogether. There will always be a loss, right? If I will like just simply search scree plot, right? Let's see what people are getting in general when they are making this plot. See, these are number of principal components. Don't you think that here we have some information loss? Or
Yeah.
here we like everywhere there will be some information loss will be there. Okay, it's not like that one will be 60, 24, 5 and then 0. Okay, so there will always be information loss. So if not needed, we should not use PCA. Okay.
And so this PCA is applicable only for linear dataset problems that you said, not for the non-linear.
No, actually for non-linear also it works fine. Uh, like the thing is that we are trying to rotate the axis in such a way that we are being able to reduce the importance of variables, right? As I said,
Mm.
uh, it can happen that maybe, and that it might not be as good as this, right? But it might come out something like this. Okay, so
Mm.
we should give it a try. Actually, the way PCA works is very unpredictable that whether I will be getting, like, see, the problem is here when I showed you this example, this is a very idealistic example, right?
Yeah.
In general, the data is not like this. right? In real life, the data will be very scattered. A lot of many things will be happening. And because principal components is not taking only two variables at a time, it is taking all the variables at the same time. In 2D, it is looking like this. But if you have three variables, the data will be distributed in 3D, like here. I think we did one yesterday, right? Where it is. Here, right? Now, just tell me, like, but just by looking at this data, how can we say that what is linear, what is not linear? And this is just in 3D. Now, just imagine if the data was in 4D, 5D, 10D, right? You just don't know how rotating the axes will give you different principal components.
Okay.
Okay, so you are just assuming as of now only two variables at a time, and then we are commenting that only for linear maybe it will work and maybe for non-linear it will not work, right? But PCA is not taking two variables at a time. PCA is taking all the variables at once. Okay, so then how the data will look like, we don't know.
Okay. So are there any chances that after doing PCA, the model of accuracy will come down, when compared
Yeah,
to
it will
using the,
actually, it will definitely come down.
I
But
mean,
by
when
how much
compared
it
to
will,
the original,
uh-huh.
let's say we have set 100%, okay, for PC1, PC2, PC3, and PC4. Like all these four principal component variables are selected, and when compared to individual variables, individual features. So is there a chance that the accuracy will still come down, I mean, even after setting it to 100%, the PCA?
If you will get the 100%, then accuracy will be more or less same.
Okay.
Only if there is an information loss, then there will be, the accuracy will come down.
Okay. Are there any similar techniques, like other than PCA?
PCA is the most popular one, but I'm not aware of it, right? But I'm damn sure there will be, right?
Okay.
Because for everything can be done in multiple ways. Like for example, for linear regression also we have like multiple variations. So I'm pretty sure there will be more variation to PCA. It's just that I'm not aware of it. But yeah,
Okay.
this is the most popular one for sure.
Okay.
Okay, done. Any other question, anyone? Okay, just give me 1 minute. Give me 1 minute. Okay, the next part is gradient boost. Okay, I will try to discuss this particular machine learning technique in Excel instead of PPT. Okay, so what we will do is we will step by step, just like in ADA boost, right? We had multiple models. Even in case of gradient boost, we will have multiple models, right? And what we will do is we will actually solve 2 or 3 iterations of gradient boost, right? We will create multiple models and then we will get a final answer, right? Then what we will do is we will try to do exactly the same thing in Python as well. In Python, we always have a function, right? We will pass the data set to that function. We will mention how many iterations that we want to do. And then we will see if we are getting the same answer or not. Okay. So let's do it. Now, AdaBoost is mainly used for classification. Gradient Boost is very famous for your predicting linear targets, right? So now let's assume that these are the three variables that I have, that whether someone likes to exercise or not, whether someone is going to gym or not, whether someone drives a car or not. And based on that, I'm going to try to predict what is the age of someone. Okay. Problem statement is clear to everyone. What we are doing? We have three variables. Based on these three variables, I'm going to try to predict what is the age of someone. Okay. Now, in gradient boosting, we create multiple models, right? If you remember AdaBoost, how the first model was created, what we did to create first model?
We took
The
that decision
weightage.
stump.
Sorry, what we did?
Decision tree. We use decision stump. Like depth is only
Okay,
one.
yeah, right. And how did we selected which variable will be?
Weightage, we decided the weightage.
No, weightage we decided later.
Gini values.
Yeah, based on
Average Gini value.
yeah, just the Gini value. Yeah, exactly, the Gini value. Or based on which variable is giving you the highest accuracy, you decided to use that variable to create your first decision tree. Is that right? Okay. Here in gradient boost, it is a little different. Our first model is nothing, right, but an average model. Okay. Our first model is nothing but the average model. That is the most basic model without using any variable we will be using. So what we will do is, I'll just take an average of this column. Okay. I'll just take average of this column, and that will become my first model. Okay. After creating the first model in AdaBoost, what used to be our second thing? We used to see for which row we are being able to predict accurately, for which row we are being able to not predict accurately, right? The same thing I will do over here as well. If this is what my actual values are, this is what my prediction is, right? My error is going to be how much? Simply the subtraction of these two. Predicted minus actual. Actually, it's in general taken as actual minus predicted. So actual minus predicted. Although it will not matter, I will take a square of it. Okay. So the first step is to create an average model. Once the average model is created, I will calculate the error. Error is nothing but actual value minus predicted value, right? But in case of linear regression, by linear regression, I mean when you have a continuous target. In case of regression, when you have a continuous target, do we calculate error like this? Or no?
No,
What is
we
what is the problem in having error like this? The errors
we
will
calculate
It will
Uh-huh.
cancel out.
RMSE. Yeah, RMSE we use.
We will
means
do RMSE, right? Because otherwise the variables will errors will cancel out each other, right? We take a square of it, right? We will take a square of it, so we'll just multiply it. Whenever we want to remove sign anywhere in stats, what do we do? Sorry. What do? We take a square. Done. And then I will take a average of it. if you look at it. So this is giving me MSE, mean square error. What is RMSE?
Root mean square.
Root mean square error.
Right. So what if I want to calculate RMSE over here? I will just take, I'm not sure. Yeah, square root function is there.
MSC.
Yeah, I will just take a square root of MSC. I will get, this is my RMSE value. So if I will use the most basic function, sorry, most basic model, my average model is considered as the most basic model. If I will use that, my RMSE value is 23.9. Right? So this is the first model. But obviously, in case of boosting is what kind of modeling technique? Ensemble modeling technique, right? Ensemble modeling technique means that multiple models will get created. If I want to create multiple models, this is the first model that I've created. What is going to be my second model? My second model is, first of all, my target variable will change. I will not try to predict age. I will try to predict the error itself. Okay. In first case, what we were trying to predict? Age. Now, after building model 1, this was my model 1. Right? Let's maybe give it. This was my model 1. After creating model 1, I calculated the errors. And once I have calculated the error, okay, what I'm trying to do is, I'm trying to predict error. Okay, so what I will do is, just 1 minute. If I'm trying to predict this, let's say, okay, let me ask it this way. Let's say you have male, female, male, female, and this is the height. Okay, and height is, let's say, 165, 168, 145, 155, 160. Let's say this is what we have. I am asking you to create a model to predict height using this data set. This is your input variable. This is your target variable. What is going to be your prediction over here? Can you tell me what is going to be the prediction for this person?
Average of males.
Average of males, right?
Yeah.
Average of males, that is these two and this. This is going to be the prediction for males, and for female, prediction is going to be average of female, right? Right. So whenever we have input variable as categorical and my target variable is continuous, this is how the prediction happens. Okay, fine, that's correct. Any doubt here? Now, going back to this, my target variable is what? Error 1. Now I will see if I will use like exercising as my input variable, or if I will use go to gym as my input variable, or if I will use drive a car as my input variable. If I will take one variable at a time, which variable is being able to predict error most accurately? Okay, so for example, for like exercising, I have two values, true and false. The prediction for true, wherever the like exercising is true, is going to be, let me show you. See, I have taken the average of wherever the value of this particular variable was true. Similarly, for false, I have taken the average of wherever the like exercising value was false. So 17 will become my prediction wherever the like exercising is true, that is green. And minus 21 will become my prediction wherever the like exercising is false. Any question here?
Puneet, can you come again? So is it
Yeah.
this one mean of it of all the true false error or how it is?
Yeah, right, exactly. That's what it is. For wherever like exercising is true, look at it once, right? This row because like exercising is true, and last 4 rows because like exercising is true. So average of all the truths will become prediction for wherever it was true. It's like for example here, wherever it was male, I had one prediction, right? And wherever it was female, I had another prediction. Right? The same way, wherever I have true, I have one prediction, which is nothing but the average. Wherever I have false, I have one prediction, that is the average. Now for this column, if I will use like exercising as my input variable, this prediction will be minus 21, minus 21, minus 21. This will be 17, again minus 21, 17, 17, 17, 17. If I will use like exercising as my input variable.
Now, why that came out to be negative? Any reason?
Because the error is sometimes positive, sometimes negative, right? So if you will take an average, that average can be negative. Any question? The same thing I will do for go to gym variable as well. Wherever it is true, I'm gonna take an average of that. See, wherever the go to gym is true, the first, I believe, 5 rows, and then the 7th row, 5 rows and the 7th row. And wherever it is false, I will take an average. So wherever go to gym was true, this will become, this minus 12 will become my prediction. And wherever go to gym was false, this 24 will become my prediction. And same goes for drive a car as well. Wherever drive a car is true, my prediction is true, 2. Wherever it is false, my prediction is minus 3. Any questions so far till this point? How we have populated
It is
this
taking
table?
average of this error column, error 1 column.
Yeah.
How we calculate this error 1?
By taking difference of our first prediction and the actual value.
Okay.
Okay. Any question? Any other question?
What is MSC of M1?
MSC of M1, where it is?
H column.
This is, yeah. This one, no? Right?
Yes.
Yeah, this is nothing but mean square error. This is nothing but average of this. And what
So
is this? This is
the
nothing but
column
square.
names are confusing, sir. MSC of M1, MSC M1. Can you please rename those? The column names, MSC of M1.
Okay.
28th row, so 28.
Yeah, let's call it then square error.
Yeah.
Okay. Cool. I'm removing this. Okay, now once you have populated this column, this table, I will check that if I will use like exercising as my predictor, as my input column, what is the accuracy that I'm getting? If I will use go to gym as my input column, then what is the accuracy that I'm getting? If I will get drive a car as my input column, what is the accuracy that I'm getting? So I will calculate square error. Okay. What is square error here? Nothing, but simply the predicted value minus the actual value and taking a square of it. Okay. Similarly here, the same thing I will do over here as well for go to gym. The actual value minus the input variable and taking a square of it. And then I'm calculating what is the MSC for like exercising by taking an average of this. Similarly, what is the MSC for go to gym? What is the MSC if I would have used drive a car as my input variable? And where I'm getting the least error, I'm getting least error for like exercising. And that's why this variable will become my input variable for the next model, because I can take only one variable at a time, just like AdaBoost. In AdaBoost, you can take only one variable at a time. Here also, I can take only one variable at a time. But here, what I will be doing is, okay, I'm first checking which variable is going to give me the highest accuracy. Highest accuracy means least error.
Here, I mean, I didn't understand like why we have to subtract the error one and like exercising. What's
Because
the
error one is my what now? My target variable. This is
yeah,
what my prediction is. So how would you know which variable is giving you the better accuracy?
okay.
Right? By calculating the error, right? So prediction minus the actual value that gives you error. Here, this is something that I'm trying to predict. This is what my target is as of now.
Okay.
Okay.
So after we are subtracting these, we are also squaring them as well.
Yes.
So why aren't we getting a perfect square in the table?
Why we are not getting a perfect square? Because these values are not exactly integer.
Okay, okay.
If you will look at it,
That was confusing. Got it.
yeah. Okay.
Yes, I understood now. So in the model one, we have got the like exercising as
Mm-hmm.
the first feature. So again, we'll take the average of all those for like exercising
Mm-hmm. Yeah, let's
in the
see
next step.
what will happen in the next. So using prediction one, what was prediction one? This is our model one. You can say this is my model one. Hey, this was my model one. Which one is my model two? My model two is this. This was my target one, right? This was my target because this is what I started with. Something, yeah, like this maybe. This is what my target was. And this is going to be my target two. Okay. So using model two, I was trying to predict my target two. Now what I will do is I will calculate error. Again error. Actual value minus the predicted value. This is correct? Actual value minus the predicted value.
So what's the actual value here? Error one?
In this one, error one, yes.
Okay,
Error one.
it's
Okay.
59. Okay.
So my final prediction is going to be, let's say if I will stop my iteration here. Okay, if I like this is, I have done only 2 iteration, model 1 and model 2. So my final prediction is going to be using this is going to be my prediction 1 plus prediction 2. Okay, prediction 1 plus prediction 2. I will add both of those. This is going to be my final prediction. If I will stop doing any iteration here. Okay, let's see if we have improved our model or not. Now, okay. First, I will calculate the square error, right? Which is nothing but my actual value, age, minus the predicted value, that is this one, and take a square of it. Okay, so if I will stop my iteration here, I will get 218 as MSC. What is RMSC value? Nothing but what it was last time. What was the RMSC value last time?
41.
24, right? 23.9.
Yeah.
Let's make it one decimal point only. 24. Now it is 14. So after first iteration, if I had stopped just after first iteration, my RMSC value was 24. Now after doing 2 iterations, my RMSC value has come down to 15. Okay, so have I improved the model or not?
Yes.
I have improved the model, right? By doing 2 iteration, I was able to improve the model. Now error 2 will become my target variable. Okay, error 2 will become my target variable. That will be my third iteration. See, this is what my target is now. Again, I will do the same thing, that if I will use like exercising as my input variable, then what is the average that I have? For false, what is the average? Similarly, for go to gym, I will check what is the average of all the trues, all the false. Okay, similarly, for drive a car. Now, what I will do is I will just put the averages here. This is my prediction. These averages are nothing but my prediction. Right? And I will see that which of these 3 variables is giving me the highest accuracy. Is like exercising giving me the highest accuracy, or go to gym is giving me the highest accuracy, or drive a car is giving me the highest accuracy. So when you will calculate which variable is giving you the least error, you will realize that go to gym is giving you the least error in predicting error 2. So go to gym will become my next variable using which I will be predicting error 2. So I will just copy paste this much part. Okay. Now error 2 has become my target variable 3. Prediction 3 has become my model number 3. Okay. What is prediction 3? This. Wherever it is true, -4. Wherever it is false, then 7. Okay. Now I will calculate error 3. What is going to be error 3? Again, the actual minus the predicted value. Okay. The actual value for me is error 2 minus the predicted value is nothing but prediction 3, which is this. Are you guys being able to follow so far?
Yes.
Yeah, yeah.
Okay. Final prediction is again going to be nothing but summation of all the prediction. So prediction 1 plus prediction 2 plus prediction 3. Okay. If I'll add all the 3 predictions, that will be my final prediction. I will calculate square error. Square error is nothing but my actual value, that is my actual age, minus the final prediction. If I will stop my iteration after the third model, then let's see what we will get. MSC after third iteration is 194. RMSC is going to be
13.9.
I think I did something wrong. What I did? Square root I did.
Root.
Square root. Square.
Okay, 14 point something. Right, 13.9. And here it was 15. 14.8. So RMSC has gone down after the third iteration.
Yes.
Right? Now the same thing. What will happen? Error 3 will become your target variable. Right? This thing will become your target variable. And you can keep on doing it. Right? No one is stopping you that, okay, after 3 you should stop, after 5 you should stop. You can keep on doing it till we will not see any other improvement. So error 3 will become my target variable. Again, I will use like exercising, go to gym, drive a car as my input variables and see which one is giving me the highest accuracy. And again, you will see that this time again like exercising. First time we used like exercising, then we used go to gym. Now it is not drive a car. Again, it is like exercising. It means that every time all the 3 variables have a chance to come out as an important variable. So like exercising is again coming out as an important variable. Okay. I will just copy this and paste it here. Okay. Error 3 was my target variable. This is my new target. And this was my model. Okay. Now my error is going to be what? My error is going to be error 3
minus prediction 4.
Very nice. Okay. Final prediction is going to be sum of all the predictions. So prediction 1 plus prediction 2 plus prediction 3 plus prediction 4. This is my final prediction. And then my square error is going to be actual value.
Sir, what is error 4 here? Can you please explain?
Just one minute.
Just the equation.
Yeah. Error 4 is nothing but error 3 minus prediction 4.
Error 3 minus prediction 4. Okay, okay. Please.
Right? This was our target variable in the previously, error 3.
Yeah.
Right? And this was my prediction for that target. So that is my error. Now my Square error is going to be the actual value minus final prediction. If I'll take a square of it. So after, I think, these 4 iterations that we have done, we are getting MSE of 184 and RMSE is going to be square root of this. If you look at the trend, our RMSE value in the starting was 24. Then it became, let's say, 15. There was a sudden drop. Then it became 14. Right? And then from 13.9, it became 13.6. So if you look at it, with each iteration, the improvement that we are making, that is going down. Okay. So with each iteration, the improvement that you will make, that will go down. So earlier it was 13.9, now only 13.6. Right? Now error 4 will become my target variable again. Error 4 is my target variable. I will check whether, like exercising, go to gym, or drive a car, which one is giving me the highest accuracy. Drive a car is giving me the highest accuracy. So in predicting error 4. So error 4 will become my, first of all, this is my new target, which I'm trying to predict. This is target 5, model number 5. My error 5 is going to be nothing but actual value minus the predicted value. Final prediction is going to be what? What is the final prediction? How do we get final prediction?
Sum of all predictions.
Sum of all prediction, right? So prediction 1 plus prediction 2 plus prediction 3 plus prediction 4 plus prediction 5. I've done it correctly. Like, let me calculate it again. Prediction 1 plus prediction 2 plus six. Okay. Okay. So this is my final prediction. So my error is going to be the actual value. My square error is going to be the actual value minus the final prediction. And I am going to take a square of it. Okay. This MSC will be nothing but average of this. RMSC will be square root of this. Okay. 13.3. Last time it was 13.6. So again, it has reduced. So with each iteration, you can see that our RMSC is going down, and we can keep on doing it. Let's say till, either the time exhausts. Let's say I want to run the model for 1 hour. So either the time exhausts or there is no further improvement in the model. Okay. So this is what my final prediction is. Now what I will try to do is, right, I will try to show you that if I would have done the same thing in Python using the Python function, whether I'm getting the same answer or not. Okay. From Excel to Python, most probably this is the one. Okay. Again, basic steps. First, reading all the libraries, then I will upload the notebook. I've uploaded the note. I am reading the CSV file. And if you look at it, I have the same data set what I had earlier. Okay. I have the same data set that I had earlier. It's just that instead of true, false, I have 0, 1s. Otherwise, 14, 15, 16, 26, 36, 14, 15, 16, 26, 36. Right? Same values are there. What I'm doing is, as a standard practice, I am keeping all the input variables separate and my target variable separate. And then what I'm doing is I'm simply using this function, gradient boost regressor. Okay. This is nothing but the function that we are using for machine learning, gradient boosting. Maximum depth equal to 1 because, as I said, right, in general, in boosting, we use stumps. That's why maximum depth is 1. N estimator equal to 4. This is telling me how many iterations I want to do. Okay. Learning rate of 1. Just ignore that part for now. Okay. So this is number of iteration. Random state again does not matter. As I said, right, it is just a random number. Now, once I have declared this function, I will be providing my input data set and my target data set, X and Y. And finally, I will make prediction on my target variable. Right? So this is how the predictions look like. For the first person, the prediction is 22.6, then 17.3, 17.3. If you look at it, 22.6, 17.3, 73, 17.3, 54, 22, 59, then 54, 22. Like the exact same as what we have over here. Right? But just look at how much time we spent doing it in Excel versus how much easy it was to do it in Python. And especially when I want to do, let's say, an estimator equal to 100, it is impossible to do it in Excel. Here, I will be able to get it very easily. Just by changing it, let's say from 4 iteration to 10 iteration, I will be able to make 10 iterations here. Okay, but that is not possible in Excel. But at least this shows me how this function is working in the backend. In the backend, the function is working like this, the way that we have created.
Yeah, Puneet, what is that learning rate?
Yeah. Learning rate is nothing but when you calculate the error, right? Here. Whenever you calculate the error, anywhere, like for example here, whenever we calculate the error, you just multiply it with a number between 0 to 1. You choose a number between 0 to 1. Okay. Let's say you have taken 0.5. Okay. Then my prediction is not going to be 41. My prediction is going to be 41 multiplied by 0.5. Okay. So that actually slows down your total prediction. But the benefit of that is that you will be able to get to more accurate answers. Like a little. Okay, let me explain it this way. What learning rate does is, this concept is more popular in deep learning, but at a few places you might see it in ML as well. You remember this used to be the error, and we were trying to find that value of slope which will give me the least error. Remember? We were trying to find
global minima something.
yeah, right. And that concept we call it as gradient descent. Right? You guys remember? In linear regression, we discussed gradient descent.
Yeah.
I call it gradient descent. Gradient is nothing but slope. Descent is nothing but going down. So going down the slope is nothing but gradient descent. Okay. How we found minimum value over there in
Derivative,
linear? Sorry.
the derivative of the slope.
Very nice. Right? We did the derivative, and that's how we were able to find it. But many places the derivative is not possible. Okay. So what do we do? In many cases, like in a lot of other different linear regression, we do a derivative. In other cases, what we do is we start at some point, right? We randomly take a point, and that's how we start. You can start maybe here, or you can start maybe here, anywhere. So randomly we have started, and then we do different iterations, and with each iteration, the error starts going down. Okay, let's say this is the first iteration, after which the error reached here. This is the second iteration, the error reached here. Third iteration, the error reached here. Fourth iteration, the error reached here. Fifth iteration, the error reached here. Sixth iteration, the error reached here. Seventh iteration, the error reached here. Now, if I will do one more iteration, what will happen?
Error will increase.
Error will increase. Error will increase with one more iteration. That's how my model will know that I should not do any more iterations, because more iterations are leading to high error. Clear this till this point?
Yes.
Right? Now the problem happens is with what should be the size of step. If you look at over here, my minimum value was somewhere here. But is this iteration giving you the minimum value?
No.
No, right? It crossed that point and reached to a little higher value than what was the optimum value. To avoid that, what people do is they say that, okay, if you will take big steps, then this is the problem which will come. So what I'm going to do is I'm going to take small steps so that I will not miss it. I will do this. With next iteration here, 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 here. And then again, the error will start increasing. But this time you will be able to find that after this particular point, it is increasing, right? So in this case versus in the previous case, in which case you will be able to find minimum error?
This case.
This case, right? But the problem is that this case took a lot of iterations to reach here, right? This case took very few iterations, maybe 6, 7. This one take 20, 25 iterations to reach it. So this is going to take a lot of time to run versus this one. This is called learning rate. How fast you want to take, like how big steps you want to take. If you will take this kind of a step, there is a chance that you might miss it. But to be very frank, I am fine. Being here instead of being here. I'm fine being here instead of being here, as long as error is more or less same. If let's say to get this value, it's gonna take, let's say, 4 hours. To get this value, it's gonna take only half hour, or 30 minutes. So maybe I will keep the learning rate more. But when I'm making the final prediction, the final iteration, maybe I can keep the learning rate small. So big the learning rate, faster your model is going to learn, but there is a chance that he might miss on the minimum. But that doesn't mean that, sometimes people assume that the learning rate is going to be like this. If I'll take a very big value, it will become like this. No, that's not the case. Okay, it is something like this versus this. Not like this versus the other one. We do not have this big learning rate. Okay, so depends how much accurately you want to tune your model. On that, the learning rate depends. So how big this step is going to be, that will depend upon learning.
And this is applied for the final prediction model, right? Not at every step, or is it applied at
No,
every
it
step?
is applied at every step.
Okay.
Like how much big of a step that you are taking, that is nothing but learning rate.
Okay.
Starting from the first iteration to the last iteration.
But for every iteration, we got one prediction, right, for that model.
Yes.
So for that predicted model only, we'll apply 0.1, isn't it?
You were here, you randomly started, so you were here.
Mm.
Then you made first prediction and your error came down. So you will be here. You made third prediction, your error reduced. So you were here, and so on. Right? The error is going down. This is error, RMSC. It is going down.
Okay.
With each iteration.
So each iteration is one model, right?
Yes. Each iteration is one model. Yeah.
So we apply that learning rate on each model.
Yes.
It will multiply by 0.1. Okay.
Yeah.
Like instead of taking long steps, we are taking smaller steps to reach the correct global minima there at the bottom.
Right. That's correct.
Okay.
Any other question? Right. So my suggestion will be, if you just go through this Excel, there is nothing that anyone can ask you on gradient descent on gradient boosting that you cannot answer, because you literally solved gradient boosting manually yourself without using Python. So obviously there cannot be anything that someone can ask you that you might not be able to answer, as long as you understand how this Excel is working.
Yeah, so please share this Excel sheet with the solved one, not the plain
right.
one, so
Sure.
that analysis becomes easy.
Sure. Yeah. The same Excel I will share, the one that I've discussed.
Yeah, thank you. So do you have similar Excels like for other ML algorithms like decision tree, Adamos?
No, if you remember, in decision tree we had an Excel, right? We discussed, where we manually calculated for each what is going to be my first split, second split, cricket versus not cricket.
Okay. I
Right?
think we
But
have
then
it
we
in the
did
one drive.
then we did it in Python as well. Yes. Similarly, if you remember, for linear regression also, when we were solving for linear regression, we used one data set, and we manually tried to find what is going to be the slope and the intercept of that linear regression, right? Yeah, so even there we did it. So wherever possible, we have done it, right? But this way, actually, I'm using Excel over here because when I used to explain it in a PPT, it used to become very, very difficult. Because if you look at it, it's very difficult to explain that there's going to be one more iteration after this. Okay.
So one question here. So we didn't apply any learning rate, right? So
No, we didn't.
how did we got the answer similar to the Python code?
No, so we like when we didn't apply, it is same as applying learning rate of 1.
Yes, yeah.
Okay. So because we have not applied, so we are getting the same answer for the learning rate as 1.
Oh, okay.
Okay. So if I will change this number, let's say to 0.5 to 0.8 or something else, then I will not get the same answer as what I was getting in Excel.
Yeah, understood.
Cool, guys. Let's take a 15 minutes break. I'll see you at around 11:05. And after that, we will discuss Bayes theorem. Okay. We'll start with my Bayes now. Okay, cool. So a naive-Bayes classifier is actually based on the naive-Bayes theorem. It's a very easy, very straightforward one. So let's start. So if you remember, the naive-Bayes theorem was something like this: the probability of B given A. Anyone remember what was this?
Yeah.
Probability of it
B given A.
A intersection A union B.
Probability
Yeah.
of B upon probability of A into
Mhm.
probability A slash
Probability
B.
Mhm.
Probability of B into probability
of A union B divided by probability of A
probability of A.
It was probability of B.
into probability
A
of
by B.
A given B
A
on
given
probability of A.
by probability of A.
Yeah, like I at that time said that always remember it like this, that if the B is here, the B is going to be in the starting as well, right? Something like this. Like you can make your own some theory around this, right? But probability of B given A is equal to probability of B multiplied by A given B divided by probability of A. Now, the same thing when we look at from a classifier perspective, it becomes more like this. Probability of, let's say, y equal to default, or let's say y is defaulting on loan, or probability of, let's say, someone having diabetes, anything that you want to call it. Or here, I'm going to use default, right? Probability that someone will default given all the input variables that we have. Knowing the value of input variables, I want to find out what is the probability of default is going to be. If you'll go by this, what it is going to be? Probability of, what should I write here?
By default.
Probability of
Of
default.
Y. Default, that is.
probability X.
Of default multiplied by probability of
X given
Given
default.
default.
given y is equal to default
And
Dot-
probability of X.
divided by probability of x, right? So now it's a little complex as compared to, what we were writing before, probability of b given a and all of that. Now, when I will take an example, I think it will become much more clearer. Here, this is just for one variable. If I had one variable, let's say x1. What if I have two variables? Right? Probability, I want to know what is. I want to know what is the probability of y defaulting, because I will not have one variable, no? I will have multiple variables. Given I have values x1 and x2. Two variables are given. Then this will become probability of y equal to default multiplied by probability of x1 given that y is default multiplied by probability x2 given that y will default divided by probability of x1 probability of x2. Okay, clear? I hope when there will be three variables, you are being able to imagine how it will look like. For three variables, it will look like probability of y equal to default multiplied by probability of x1 given y will default, probability of x2 given y will default, probability of x3 given y will default, and similarly divided by probability of x1 multiplied by probability of x2 multiplied by probability of x3. Okay, if I will write, again, not needed, just remember it at a very high level, that will be fine. But if you look at it like how you will see it over the internet, right? The generic version of it, this is for one variable, this is for two variable. What if I want to write it for n number of variables? Okay, for n number of variables, this is how it will look like. Probability y equal to default given you have multiple variables x1, x2, let's say xn, will be equal to probability of y default. What is this symbol?
Pi.
Right, pi. But just like we have summation, this symbol represents multiplication. Okay, so this represents multiplication. Multiplication of what we want to do?
X of
P
I of X of I.
x of I, given that y will default. So this is a generic version. This is true for I equal to 1 as well, I equal to 10 as well, and everything. Similarly, in the bottom also, it will be the multiplication I equal to 1 to n probability of xi. Like, this is a generic version. This is how people write Bayes classifier. Okay, might look like a little fancy, right? But it's very easy when we will try to take an example. Okay, let's try to take an example. I have different variables like animals, size of the animal, body color, and finally, can we pet them or not? This is my target variable. Okay, so I have an animal like dog, rat, cow. These animals are there. Size of the animal is given, whether it is a big, small. Like for example, a big dog, maybe I don't want to pet, but a small dog, maybe I'm ready to pet. Right? Same goes for cow as well. Maybe a small or medium cow, I'm ready to pet, but a big cow, I might not pet. Something like this. Okay, and a rat, I'm not sure. I will not pet at all. Okay. So we have animals, we have size of animal, and we have the color of the animal, based on which it is given to us whether we will be petting them or not. And later in the future, let's say it will be given to you what is the animal size and body color, and then you need to predict what will happen. Okay. So let's do this. Let's first try to, before jumping onto the calculation, let's try to look at a few probabilities. For example, the different animals that I have is I have dog, I have rat, I have cow. We will see that how many yes are there, that how many dogs you can pet, how many dogs you cannot pet, how many yes we have, what is the probability of yes, what is the probability of no. Okay. So for example, for dog, how many yes are there? This is a yes, this is a no. This is a yes, this is a yes, this is a yes. So 4 yes are there, 1 is no. So what will be the probability of yes?
4/5.
4 by 5. Right. I asked the wrong question. I'll explain later. Like, what do I mean by probability of yes over here? Just 1 minute. For rat, how many yeses and how many no's are there? Let's say for rat, this is yes, this is wrong, this is not, this is not. Okay. So we have 3 no's and 1 yes. And similarly for cow, this is yes, no, yes, no. 2 yes, 2 no's. Mhm. 3 no's. Sorry, just 1 minute. I'm counting wrong.
The last cow.
Yeah, right. 1, 2, 3 no's are there, and yes,
Last cow is a
no.
yes.
Okay. So 1, 2, 3 yes are there and 2 no's are there. Okay. Probability of yes here is at an overall level. Okay. What is the probability of yes? Total number of yes that I have is 8. So probability of yes for a dog is going to be 4 by 8. So we are saying that in yes, what percentage of animals are dog? For yes, what percentage of animals are rat? For yes, what percentage of animals are cow? Same goes for no as well. I have total 6 no's. So for no, what percentage are dog? What percentage are rats? and what percentage are cow. Okay, and similarly, we can calculate something similar for other variables as well. This is just for one variable. So we have small, medium, big. And I want to see how many yes and no's are there. For small, it is going to be 1, 2, 3 yes. And how many no's are there? 1, 2. So 2 are there. For medium, let's mark it. It is a yes, yes, no, no, right? 2 yes, 2 no. For big, this is no, yes, yes, no, yes. Okay, so 3 yes, 2 no. The same thing I will calculate. What is the probability of yes over here? 3 by 8, 2 by 8, 3 by 8. Probability of no? 2 by 6, 2 by 6. Okay, so it's 2 by 6 everywhere. Okay. So at overall level, probability of yes is 8 by 14 because there are 8 yes out of the 14 total data points that we have. Similarly, probability of no is 6 by 14. Okay. I'm just thinking let's create it for the third variable as well, maybe. Just takes little time. So my third variable is the color. Let's have this table. So I'm creating this table so that when we will start imputing the values, it's very easy for us. So color that we have is, we have black color, we have white color, we have brown color. So 3 colors. Black, white, and brown. How many blacks we have as yes? 1, 2, 3. Okay, this one. Yeah, 3 yes. And then only 1, I believe, no. So 3 yes, 1 no. For white, similarly. Yes, yes, 2, 3 yes, and 2 no's. Okay, now I think we can subtract also to kind of get it. Total number of yes are 8, 6 are already covered, so 2. Total number of no's are 6, 3 are already covered, so this is 3. Okay, so probability of yes is going to be nothing but 3 by 8, 3 by 8, 2 by 8. Similarly for no, 1 by 6, 2 by 6, and 3 by 6. Now once we have this table ready, okay, and if anyone will give me what is the type of animal it is, what is the size of animal, and what is the color of the animal, right? Then I can find the probability, like what is the probability that, uh, that I should, whether, what is the probability that I should be petting that animal or not. So just for an example sake, what we will do is, let's take a value, like maybe, so we need to take one type of animal. We need to take one size of the animal. And we need to take a color of the animal. Type can be, let's say, cow. Size can be medium. And let's say black. And I want to find out whether I should be, like, what is my target variable? Whether I should pet this animal or not. Okay. Now, what I will use is I will use base classifier. Base classifier is nothing but probability of finding whether I should be petting this animal or not, given that it is a cow, it is medium, and it is black in color, right? Given these three things, that it is a cow, it is black, and it is medium in color, I want to, sorry, medium in size, I want to find out what is the probability that I should be petting it. If I will simplify this, can anyone tell me what the equation will look like?
Probability of yes
Yes, right, very
into
nice.
probability of cow, given that probability of
That
yes.
yes,
Given it is yes.
probability of
Probability medium,
medium
given that
given that
probability of
yes.
yes. Probability of black, given that it is probability of yes. Whole upon probability of cow into probability medium, probability black.
Very nice. Okay. This whole thing divided by probability of cow.
Medium and black.
Yeah, nice. Okay. Now, because what we have the table ready, you'll see that how much easy it is to impute all the values. What is the probability of yes?
8/14.
8/14. Okay. 8/14 is the probability of yes, because in the total data points are 14, out of which 8 are yes. So probability of yes in general is 8/14 here. What is the probability of cow given that it is yes? Can anyone tell me? What is the probability of cow
3
given
by
that
3
yes,
by
3
8.
by 8? 3 by 8, right? This one. 3 by 8, right? So because it is given that it is yes, so it means that I'm already talking about these 8 data points. So it's going to be 3 by 8. What is the probability of medium given
2
that
by
it is
8.
yes? Medium given that it is yes, 2 by 8. What is the probability of black given that it is yes?
Same 2 by 8.
Black given that it is, no, 3 by 8, right?
Brown, right?
Black.
Yeah. 3 by 8.
3 by 8 divided by probability of cow, probability of medium, probability of black. Probability of cow will be nothing but total number of data points, like 5.
5/14.
5/14, nice. Probability of medium is going to be total number of medium, that is 4/14, multiplied by your probability of black, right? 4/14.
4/14.
Now let's solve it. Give me 1 minute. Okay. Now, this is coming out to be, in my calculation, it is coming out to be around 0.68. Okay. Now the probability of yes, given that it is cow, medium, and black, right, is 68%. Okay. So what is going to be the probability of no?
0.32.
0.32, right? But let's calculate it. It's not going to take much time. So let's calculate it. Let's see if we are getting, 32% as no. No. Um,
6 per 14.
this will change. This will not change. Okay. Then probability of no, 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 no. So you will see that now this will look like 6 by 14. This will be probability of cow given that it is no. Probability of cow give, so 2 by 6. Okay, let's remove all of it. This is going to be 2 by 6. Probability of medium given that it is no, 2 by 6. And similarly for black as well, it is 1 by 6. Okay, let's calculate it. Okay, if you will calculate it, it will come out to be 0.27, not 0.32. Okay, so this is one thing that we need to remember. When we find out the probability of yes, it was 68%. When we find out probability of no, it was not 1 minus probability of yes, it was 27%. Right? Then from here, we need to normalize it. We will say probability of yes, given that it is a cow, it is medium, it is black in color, will be equal to 0.68 divided by 0.68 plus 0.32. Sorry, 0.27, my bad. 0.27, which is nothing but 0.71, that is 71%. Okay. Similarly, probability of no, given that it is cow, it is medium, it is black, is going to be 0.27. Zero 0.68 plus 0.27. Like this time you can easily subtract also. You will get 29%, right? Subtraction of these two. Okay, so probability that you can pet this particular animal is 71%. Probability that you cannot pet this animal is 29%. So what should be my final prediction? If there is an animal which is
Yes, can be pet.
cow, right, which is medium, which is black in color, my prediction is going to be we can pet. Okay, this is how Bayes theorem works. For each variable that you will give me, like of all the input variables that you will give me, I will just calculate the probabilities and see what is the probability of, let's say, zeros, what is the probability of 1. In this case, let's say, what is the probability of whether we can pet or we cannot pet this animal. Wherever we will get the more probability, that is going to be our final answer. Done?
Could you please show the previous slide?
Yeah, sure.
Yeah, thanks.
Nice, straightforward, nothing
Yeah.
very complex. Yeah, if you look at it from like this formula, if you will Google Bayes theorem, the formula will look something like this. Okay, so it looks a little scary, this symbol of pi, right, and all of that, but it's very straightforward. If you look at it, what it means, it's very easy. Okay. Yeah, this is what Bayes theorem is. If you have any question, let me know. Just 1 minute. Okay, if you have any doubt, that's you can ask me. Otherwise, that's all for today. I will see you guys next week. Next week, we will try to cover whatever we were not able to cover this week. I think one is SVM, one is hierarchical clustering. These are two topics that I have in my mind to cover for next week. Most probably we'll have just one more class that is on Saturday, and Sunday we can keep it off. And then the week after that, okay? So next, like this is what most probable plan is. I will check with Abhishek if he has anything else planned, but most probably Saturday we will have a class. Sunday we can give it as off, and then next week after that we can start with time series. Okay, but let's see what if Abhishek has something else in mind.
Puneet, I have a question. So while we are calculating the probability of either we can pet the cow or not, so the probability didn't add up to 1.
Right.
Why exactly? Because I don't see any, all the probabilities were independent of each other. So
Right. So actually what happens is that if you will just use one variable at a time, okay? Let's say if I will try to find the probability of yes, given that it is cow, if you will do that, then the probabilities of yes and no will add up to 100%. But as soon as we take multiple variables into account, okay,
Yeah.
then the probabilities never add up to 100%.
Okay.
Most of the time it will not. 99% will not add up to 100%.
Okay.
Okay, the equation is like that itself, you can say. But if you take one variable only, then you will see it is adding up to 100%.
Okay, understood.
So there's no Python code for this.
I have the Python code. I can share it with you. It's very, again, straightforward.
Would
Nothing
you
very.
also share the gradient boosting, the Excel
Yeah.
and the Python code?
Sure, definitely. Anything that I've covered in the class, I will definitely share on the shared drive.
Thank you.
Yeah, please do it today only, please.
Yeah, just 15 minutes after this class, you will have it.
Okay.
Cool. Thank you, guys. Bye-bye.
Thank
We'll see you
you.
next week.
Bye-bye.